Hey everyone, we are looking today at vectors and a couple important properties of vectors because they are going to be the basis for how we approach and solve projectile motion, two-dimensional motion, which we're getting to in the next couple of class days. Okay, so this is really just looking at vectors, and then we'll look more specifically at the projectile motion, the two-dimensional kind of problems coming up. But we'll be using these key ideas to guide us for solving those problems, both conceptual, but also a lot of calculation style questions. So the first thing, just a reminder, adding vectors. Okay, any vector can be represented by the sum of other vectors. A vector is something that includes a magnitude and amount, usually like the length of the arrow, as well as the direction. Here my red arrow, vector A, is pointing what? Up and to the right. Okay? I could just have this vector as up and to the right. But because vectors can be added together, I could just as well say that this vector is equal to this little dashed blue vector that's only going to the right, combined with this vector, vector C, going straight up. Okay, when you add vectors, you do like heads to tails. Okay, so this dashed line plus this dashed line, and then you draw from the two endpoints. Okay, B plus C, there is no mathematical and no physical difference between the two items. No, just for sake of argument, I don't have to use like the right triangle that I have set up with B and C. I could have one vector that's going like, oh man, like this. It's tough for me to draw a straight line. Added together with a vector like this. Okay? That also is identical to C, or I'm sorry, to this red line right here. I also could use more than one vector in adding them together. If I change colors real quick, let's see. Go to blue. I could say, ooh, this vector plus this vector plus that vector plus this vector plus this vector plus that vector. That is also equal to my red vector A. We'll usually stick to just two to keep our lives easier, and we'll actually often use these perpendicular ones for a reason I'm going to get to. But I can add up vectors. There's no difference between A compared to B combined with C. I could write them the same way. There's no difference. Well, that brings us to the key problem we might have in this class when it comes to looking at a wide variety of motion. Because sometimes things aren't simply moving to the right, and sometimes things aren't simply moving upwards. They might be moving up and to the right, like vector A here. Okay? Because it's identical to say that vector A is equal to B and C added together, and B is already in a direction we're used to, horizontal, and C is already a direction we're used to, we have experience with, vertical motion. Okay, we won't just look now at this new up and to the right direction. Instead, we will do what's known as breaking vectors into components. We will always break vectors that are not in the horizontal and vertical direction into those components. Okay, because that way they are in forms that we are used to seeing. It's easier to apply our equations for constant acceleration, for example, for B and C, just because we've done this already. Okay? And that's really helpful if we have a problem when there's vectors in all different directions. If there one's like that, and one like that, and one like that. Okay? You have to somehow stay organized. And so if we always break them into left, right, and up, down, that way we'll be able to add those vectors as necessary. Okay? So we will often be breaking things into components, and that's easy to do. Okay, especially if you know our angle theta. If we know this angle, if we know one of the angles of the triangle, we're able to use our SOHCAHTOA. That's another reason why we would use these perpendicular ones, because this is a nice right triangle. If I know what theta is, if I know what A is equal to, then I could solve for B or C pretty easily. Next point, and this is an important one for projectile motion. Okay. If vectors are perpendicular to each other, they do not affect each other. They are independent of one another. And I have an example. Let's say I have this green vector. Maybe it's a velocity vector, whatever. You're moving to the right. Okay? And to that, I add another horizontal vector, yellow. It's like you're moving to the right, and then you actually gain a little bit of velocity to the right, if you want to think of it that way. Well, when I add them up, I do head to tails, and that gives me, no surprise, a larger horizontal vector. Now I'm moving faster to the right. The length is longer. I was moving to the right. I'm moving a little more to the right in the same direction. They add up. Okay. I have changed the original. My original one was this length. My original velocity was maybe 5. Now I've increased it. It was 5 plus whatever that yellow one. So in total, I don't know, maybe it's 8. You pick a number. Okay, I've changed that original vector because I added one in the same direction. Let's say now I don't add one that's acting in the same direction. I add one that's acting perpendicular, up and down. Well, same thing. You do head to tails. Now when I add those up, just like we saw on the previous screen, I get this up and to the right. But here's the key thing. Looking at this vector here, it still has that same green length horizontal vector. Unlike up here, where the horizontal vector got larger, this one stayed the exact same. If you were moving to the right at 5 meters per second, and then you started moving upwards at, I don't know, 2, whatever, at the end, you still have, if we broke it back into components, the same length, the same horizontal velocity. That did not go away. Adding this vector here in no way changed this vector. Okay, that's true for any type of vectors we're adding up. Okay, if they're perpendicular to each other, even though we can add them, even though we can say they're equivalent, this is still equivalent to this one. We did not fundamentally change the original vector that we had. Nor did this green one change this maroon, this purplish one. Okay, they stayed their original size. So, if needed, any vector that's at a weird angle, not simply to the left or right and not simply up or down, we're going to break into x and y components. Okay, we can do that for 3 reasons. The first, it's because that's what we're used to seeing. Like I said, we've seen horizontal motion, we've seen vertical motion. So it's common. We've seen it. We've done it before. It also is going to set up some nice right triangles. Okay, if we're always breaking things into x and y, I can use SOHCAHTOA as long as I know some angles. And also, the last reason, these perpendicular directions can be treated independently of one another. Okay, I do not have to worry when I break them down into x and y that I am somehow affecting the x and y properties. They are separate, which that last example hopefully showed you. The last thing I want to show, okay, if we look at kind of all the variables we've seen so far over the last week or so, we have vectors that are like these arrows, and we have scalars. Scalars do not depend on direction. Okay, acceleration, we'll see. Okay, it's a vector. Velocity is a vector. Displacement is a vector. Direction affects all of these. Something accelerating to the left is very different than something accelerating to the right. Time is not a vector. It does not depend on direction. The key thing when we're doing projectile motion is that time can be used in either the horizontal, oh, that was a poorly drawn line, or the vertical, because it doesn't matter. Time is kind of our key. Time allows us to transcend, if you want. We can transcend the 2 directions because it's okay. Usually in our problems, it is often a goal to solve for time. Because if I can solve for time, I can apply it both for things moving horizontally and to things moving vertically. Okay. Anyway, that's it for vectors. Thank you.